In this video, we are going to talk about a question on the Leetcode website, the question number 1293. The question is as follows. Given an m by n matrix representing a maze and given a value k, our task is to return the minimum number of steps from ij equals 0, 0, which is the upper left corner, to m-1, n-1, which is the lower right corner. There are some rules in this question. The first rule is that one can move right, up, left, or down at each step. So this indicates all the possible directions you may move. The second rule is that each cell in a matrix will be 0, which refers to empty, or 1, which refers to the obstacle, and we will explain what this obstacle means later. The third rule is that the total number of obstacles in a path has to be less than or equal to k. In other words, k is the maximum number of obstacles you can eliminate along your path. Let's try to see an example to illustrate what is the meaning of those rules. Firstly, each cell in this 5 by 3 matrix will contain 0 or 1. Since 0 refers to empty, for simplicity we ignore 0 for a moment. Next, imagine we are an apple lying on the upper left corner. Our goal is to arrive at the lower right corner. Since 1 refers to an obstacle, that means we cannot directly pass through those ones in this matrix. One obvious strategy is to move as follows: right, right, down, down, left, left, down, down, right, and right. There are in total 10 steps in this path. However, we are also given a value k, which indicates the maximum number of obstacles we can eliminate along our path. Let's say k equals 1, for example, which means we can eliminate at most 1 obstacle during our path. If we choose to eliminate this obstacle, that means our path can be as follows: down, 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 right, and right. In this path, we have in total 6 steps. In summary, if our input is A equals this 5 by 3 matrix and k equals 1, which means we can eliminate at most 1 obstacle in our path, our task is to return 6, because 6 is the minimum number of steps we can achieve in our path. On the other hand, if our input is A equals this 5 by 3 matrix, but k equals 0, which means we cannot eliminate any obstacle in our path, our task is to return 10, because 10 is the minimum number of steps we can achieve using our path. In order to make sure you know what's going on, I'm illustrating another example here. Let's say we have another 5 by 4 matrix A. Assuming k equals 0, we should return -1 because there's no possible path without eliminating any obstacles, and -1 refers to impossibility. However, if k equals 1, we should return 7 because along this green path, we can achieve 7 steps with eliminating 1 obstacle. Similarly, when k equals 2, we should also return 7 because along the same green path, we can achieve 7 steps with eliminating 1 obstacle, and 2 is the maximum number of obstacles we can eliminate. So you can expect that when k is greater than 2, we should always return 7. For this kind of questions where we have to find the minimum steps of a path in a maze, we usually apply a strategy called breadth first search, or BFS. In this strategy, we create a container called queue where we can push a new item from the end of queue and pop out an item from the front of queue. In case you are not familiar with what is a queue, let me explain how a queue works. For example, we can push apple 1 first, push apple 2, push apple 3, and then pop. After these sequential commands, we will have only apple 3 left in the queue. Your apple 1 to apple 3 may contain different pieces of information. Whenever you are pushing an apple, you are adding a new apple from the end of queue. Whenever you are popping, you are erasing the apple at the front of queue. After knowing how a queue works, let's see how we can apply this queue to our maze question. Firstly, our apple should start from the upper left corner of the maze, and we can push a new apple to the queue to represent our situation. Naively, we have 4 possible directions from the first apple, but only 2 of them will work since we cannot get out of the matrix. That means we can either go right, where we push the second apple to the queue to represent this situation, or we can go down, where we push the third apple to the queue to represent this situation. Since we are done for the first apple, we pop out the first apple in the queue. So the next step is to consider the second apple, since that is the first item in the queue. Similarly, we have 4 possible directions from the second apple, but only 3 of them will work since we cannot get out of the matrix. This means we can either go right, left, or down, and we have to push 3 more new apples to the queue. This roughly describes our strategy for this problem, but the only remaining question is, what is the correct information we have to store in each apple in a queue? Obviously, the position is part of the information we should store because we have to know the position to discuss what are the all possible directions from the corresponding apple. So the question becomes, in addition to the position, what is other information we should store? Remember, we have to store something related to k because k is the maximum number of obstacles we can eliminate. I suggest you can pause the video and try to think about the answer by yourself. Here we will present 3 kinds of solutions, from basic solution, slightly better solution, to the best solution. For the basic solution, the stored information in each apple in the queue will be position, can eliminate, and steps. Here, position records the ij position of the apple. Can eliminate starts from the given k and decreases by 1 whenever the apple passes through the obstacle. The steps variable records the total number of steps starting from the very beginning. Here is an example to illustrate this idea. Firstly, our apple starts from the position equals 0, 0. Can eliminate is equal to the given k, which is equal to 1. The steps variable starts from 0. Our first apple has 2 possible directions. If we go right, we push the second apple to the queue. The position becomes 0, 1. The can eliminate remains the same because we do not pass through an obstacle. The steps is increasing by 1. On the other hand, if we go down, we push the third apple to the queue. The position becomes 1, 0. The can eliminate variable decreases by 1 because we are passing through an obstacle. The steps variable is increasing by 1. This process continues, and at some point, we will arrive at the position 3, 2, where can eliminate variable equals 0 and steps variable equals 5. Naively, we may have 2 possible directions which are going down and going left, but actually we cannot go left because our can eliminate variable equals 0 and we don't have enough quota to eliminate another obstacle and go left. If we go down from here, we will arrive at the lower right corner, which is 4, 2 position, and our steps will become 6, which is the final answer. There are 2 issues here. The first issue is that we may encounter a going back and forth problem. Let me use an example to illustrate this issue here. Firstly, we start from the upper left corner. We have two possible directions, which are going right and going down, so we push two more apples to the queue. We are done with the first apple, so we pop the first apple out. Secondly, we focus on our second apple, which lies on the position 0, 1. One possible direction from the second apple is going left, so we push the fourth apple to the queue. Now we can see the problem. The fourth apple in the queue has the position 0, 0, which is exactly the same as the first apple, but the fourth apple has a larger steps, so this fourth apple cannot be the desired path. In other words, how do we get the fourth apple? It's just by going right first, and then going left. This obviously cannot be the optimal path, so I call this problem as the going back and forth problem. The way to solve this issue is by adding another variable to the stored information, which is the direction variable. After we have the direction variable, we verify at each step that we do not turn 180 degrees. In other words, if the previous direction was going right, we will not consider going left as a possible direction. So including the direction variable is our slightly better solution. Here is the second issue. Let's say we start from 0, 1 and we want to arrive at 0, 2. We have two possible paths here. The first green path is directly going right. The second blue path is going down, right, and up. Obviously, we do not want the blue path because the blue path takes more time and the blue path passes through more obstacles. So the second issue is how do we get rid of this blue path and give this blue path an early stop. I suggest you pause the video again and think about the solution by yourself. The solution to this issue is that we can construct another two-dimensional array called capital A, where Aij stores the can-eliminate variable of the corresponding apple whenever this apple arrives at the position ij. Let me use this green path and blue path to illustrate how this Aij works. If you think about this BFS strategy or queue strategy, you will find that we will arrive at the green path first, because green path takes fewer steps. Since this green path ends at 0, 2 position with can-eliminate variable equals 1, we update our capital A 0, 2 to be equal to 1. Later in the queue, the blue path will be considered, and since this blue path also ends at 0, 2 position, but with can-eliminate variable equals 0, we stop the blue path and get rid of this blue path. In other words, if a path ends at the ij position at later time, but with a lower can-eliminate variable, we get rid of that path. As another example, let's say we start from position 0, 0, and we try to achieve 2, 0. Similarly, the green path will be considered first because it has fewer steps. Since our green path passes through one obstacle, its can-eliminate variable will decrease by 1, so the can-eliminate variable equals 0 when it reaches the 2, 0 position along the green path. Therefore, we will update our capital A 2, 0 to be equal to 0. On the other hand, the blue path will be considered at later time, but its can-eliminate variable does not decrease since it does not pass through any obstacle. That means, along the blue path, the can-eliminate variable equals 1 at 2, 0. Since 1 is greater than 0, we will update our capital A 2, 0 to be equal to 1, and the blue path is still considered as a potential candidate. In summary, if our blue path at later time has a higher can-eliminate variable, we continue considering this blue path as a candidate. On the other hand, if our blue path has a lower can eliminate variable, we get rid of this blue path. As an analogy, our green path is like an Uber, and our blue path is like a bus. Uber takes shorter time and bus takes longer time, which corresponds to green path takes fewer steps and blue path takes more steps. We will want to make sure the bus will cost less in order to be considered as a candidate, because if the bus costs more than Uber, we will take Uber instead. After performing this capital AIJ strategy, we can achieve our best solution. Thank you for your watching. I hope you enjoy this video.